So this is the continuation of the vibrations lecture. Up to now we have discussed about mainly free vibrations, okay, free vibrations and free damped vibrations. So here the term free suggests that no external force is acting on our system, okay, no external force is acting on our systems. Now today we are going to look at underdamped forced vibration. So if you can recall, in the last lecture you learnt about three types of damped vibrations, right? You have overdamped, underdamped and critically damped. And out of these three cases, both the overdamped case as well as the critically damped case are known as aperiodic. Aperiodic means they are not periodic, okay? Therefore we'll be looking at the underdamped forced vibrations. So forced vibration means an external periodic force is being applied on our system. So this figure must be a bit familiar to you. You have a spring, a damper and a mass has been attached to it, and initial displacement of x has been given to the mass, okay, and you can see a free body diagram of the mass as well, indicating all the forces acting on the body, right? And take a look at the notations here. The external periodic force is denoted as Fx, and Fx is equal to F cos omega t. So in this expression you can see that here capital F is the static force and it is a constant value, okay, and Fx becomes periodic due to the cos omega t term. So you can see that although capital F is a constant value, when the time changes, when the t value changes, what happens is Fx changes accordingly, right? And the other term is omega. You are familiar with this already. It is the angular velocity of this periodic force. Now let us derive an equation for the motion of this forced vibration system, okay? So at some time t, the mass is displaced downwards through a distance x from its main position, and this displacement happens due to this applied periodic force, okay, which is Fx. And using the symbols as discussed in the previous article, the equation of motion may be written as, so you can write the equation of motion this way. So we are applying F equals ma downwards, okay. So what are the forces acting downwards? So here both the Sx and C dx dt, this is the damping force. These two forces, spring force and the damping force, are acting upwards. Therefore in this equation, so we are applying this downwards, okay. F equals ma downwards. Since these are acting upwards, they are denoted as negative values, and our periodic force is acting downwards at this moment, okay. That is why the system is displaced by x downwards, okay. Therefore it is plus positive F cos omega t or positive Fx. So you can simplify the equation as this way. So we have all the x terms on our left hand side and the t term in our right hand side. So these are left hand side, you have a function of x, whereas your right hand side you have a function of t. So this is your equation 1. This equation of motion may be solved either by differential equation method or by graphical method as discussed below. So let us see how to solve this equation. So our equation 1 is a differential equation of the second degree, and the right hand side is a function of t, right? So normally the solution of this type of a differential equation consists of two parts. One part is known as the complementary function and the other part is known as the particular integral, okay. If you can recall, when we discussed about this underdamped vibration, we derived a term for the complementary function, and it is shown as equation number 2. Since you have the lecture slides with you, you can go back and refresh your memory regarding this derivation. Okay. Find out how to derive the particular integral. We have assumed x2 or the particular integral as b1 sin omega t plus b2 cos omega t, where both b1 and b2 are constants. Okay, so we can find both dx over dt as well as d squared x over dt squared terms by using this relationship. Now we can substitute the expressions we derived for both dx over dt and d squared x over dt squared in equation 1. This is what we get, and we can further simplify this. Now we can see you have sine terms, cos terms spread everywhere within this expression. You can further simplify this as an addition of sine omega t term plus cos omega t term, right? Then so in your right hand side also you have a cos omega t term. What we are going to do now is, we don't know the values of b1 and b2. These two are constants, right? And in order to find these constants, what we can do is we can equate the coefficients in both left hand side and right hand side, right? So therefore we can, although we don't have a sine term on the right hand side, what we can do is we can use we can write a sine omega t term, the coefficient as 0, right? And so by comparing the coefficients, we can get the equation number 3. So first we have compared the sine omega t terms, right? So your right hand side is 0 and you get this expression. It is your equation number 3. And the second one is by comparing the cos term. Okay, now you can see by using your equation number 3, we can easily get a relationship between b1 and b2. Okay, b1 and b2 using equation number 3. So here they have found an answer for b2 in terms of b1, right? Now what we can do is we can go and substitute this b2 value in our equation number 4. Okay, then we get this equation where our only unknown term is b1. By using this equation, we can find the value of b1. So now that we have found the value of the constant b1, what we can do is we can go and plug this value in our equation 5. Okay, because equation 5 is a relationship between b1 and b2. So by plugging in this value in equation 5, we get the value of our constant b2, right? Now what we can do is we have found both the b1 and b2 values. Now we can go and substitute these values in our particular integral expression like this. Okay. Now when we observe this expression, we can see that this f over this term is common to both these two terms, right? It is common. Therefore we can take that part out and further simplify this equation in this manner. So we have named it as equation number 6. Here we have a sine term as well as cos term. Let us see how we can further simplify this one. I'm going to take c omega as x sine psi and s minus m omega squared as x cos psi. So by squaring these two terms, you can find the value of x, right? And also by dividing these two, you can find the angle psi. And so let's see what happens when we substitute these two in our equation number 6. We get this form, and we can write this as cos omega t minus psi. Okay, because what we have here is a cos a minus b type, sin plus cos. Now that we know the value of x, we can substitute the value of x in here and get this answer. So we can write the complete solution in this manner. Here you have the complementary part, here you have the integral part. Okay, complementary part, integral part. Although we have our solution consists of two parts, the complementary function and the particular integral. Any given time, the complementary function x1 is much smaller compared to the particular integral. If you can go back and take a look at the complementary function, it has this e minus at term. At a given time, that term is going to give you a much smaller value. Hence, we can neglect that term and write the solution in terms of the particular integral alone. And the simplified version is shown in equation number 7. Okay, so this equation shows you that the motion is simple harmonic and the angular frequency is indeed omega. And what is this term here? This is your amplitude. Okay, this is your amplitude. Amplitude is the maximum displacement. The frequency of the forced vibration is indeed equal to the angular velocity of the periodic force, which is this one. So it is the same. X max is the expression we derived for our amplitude. Okay, and here what we have done is we have divided both the numerator and the denominator by s. Okay, by s, and we can simplify the numerator as we know that f equals sx naught, right? Therefore we can write f over x as x naught, and here x naught is said to be the deflection of the system under the static force F. Static force F means it is not a periodic force, just the magnitude of the force is F, and it is not periodic. That is why it is known as static force. Okay, and we know that the natural frequency of free vibration is given as this. You know that natural frequency of free vibration is SOM square root. Okay, now here we have an S term and an M term. By dividing S by this M, we can plug in this omega n value in here. Now let us see what happens when there is no damping. Okay, so when the damping is negligible, this C is 0, right? So you can substitute C0 into the equation number 9 and you will get this. Okay, the simplified version of the amplitude expression, right? They have multiplied both the numerator and denominator by omega n squared, and in place of omega n squared they have substituted S over M in here. Okay, and you know that the spring force equals to F equals Sx naught. Therefore they have substituted F in place of x naught, right? And this is what you get for the amplitude when the damping is negligible. And at resonance means when the angular frequency is equal to the natural angular frequency of the free vibration, that is omega equals omega n, right? So when this happens, our omega is equal to SOM square root, and by substituting omega equals omega n in your equation 9, you get this expression for your amplitude. Okay, now let us take a look at the magnification factor or dynamic magnifier, and it is defined as the ratio of maximum displacement of the forced vibration, which is x max, to the displacement due to the static force F, and which is x naught. Okay, so it's the ratio between x max and x naught. So in the previous slide we derived this expression, right? And by taking the x max over x naught ratio, we get the dynamic magnifier. And here you see that if you observe these two forms, you can see in the bottom one you have the critical damping coefficient included as well. So what they have done is, here from here to here, they have used these two relationships. This one is omega n, you know, omega n squared equals s over m. They have used this one as well as the expression of the critical damping coefficient, 2m omega n. Okay, so by using these two, we can get from here to here. So just know that the magnification factor is the ratio between the amplitude of the forced vibration to the displacement due to the static force F. Now if you know the magnification factor and the static deflection produced by the force F, then by multiplying these two, you can find the amplitude of the forced vibration. Okay, by using this expression. Okay, so here we have some special cases. Case 1, if there is no damping, what happens? When there is no damping, C is 0, the damping coefficient is 0. So by substituting C0 in the magnification factor relationship, you can get this expression. Okay, and at resonance means when omega equals omega n, you can substitute omega equals omega n in the magnification factor relationship, and you will get this S over C omega n. Now you have learnt about longitudinal vibration and transverse vibration. Okay, now we move on to torsional vibration. So now let's take a look at the definition. When the particles of a shaft or disc move in a circle above the axis of the shaft, then the vibrations are known as torsional vibrations. And in this case, the shaft is twisted and untwisted alternately, and torsional shear stresses are induced in the shaft. So that is what happens in torsional vibrations. And let's see the natural frequency of free torsional vibrations, and take a look at the figure given. The disc is attached to a shaft, and let's take a look at the notation. Theta is the angular displacement. So in linear vibration, we considered linear displacement. Now here we consider the angular displacement, and it is denoted by theta. Then m is the mass of the disc in kilograms, I is the moment of inertia of the disc, then k is the radius of gyration in meters, then q, simple q, is the torsional stiffness of the shaft. So in linear vibration we use S, which is the spring coefficient. Here we use the torsional stiffness of the shaft. Okay, q. Now let us derive an expression for the torsional vibration of the shaft. So here when we give an initial angular displacement of theta from the mean position as shown in the figure, the restoring force is q theta. So it is similar to Sx in linear vibration. Here we use q theta, and the accelerating force is I into the angular acceleration, I into the angular acceleration. Okay, then so these are the two forces acting on the disk, therefore we can equate equation 1 and 2. But here's the thing, take a look at the, try to understand the direction of these two forces. When we equate the equations 1 and 2, the restoring force is used with a negative sign, okay, because it is acting in the opposite direction to the accelerating force. Okay, then we can take this q theta term to the left hand side, and we end up with this equation, d squared theta over dt squared plus q over I into theta. Okay. The fundamental equation of the simple harmonic motion in torsional vibration can be written this way: d squared theta over dt squared plus omega squared x equals 0. So you are familiar with this equation already. That so in place of x we are using theta, because here we are dealing with angular displacement. Okay, so when we compare equation 4 with equation 3, you can write an expression for omega squared. Omega squared equals q over I, right? Therefore omega is square root of q over I. Now we know how to get the time period. Time period equals 2 pi over omega. Then since we know omega, we can get an expression for the time period as well. Then how to get natural frequency if we know the time period? So natural frequency equals 1 over time period. Therefore you can get an expression for the natural frequency as well. Well, let's say if you don't know the torsional stiffness Q, then by using this torsion equation given here, you can easily calculate Q as well. So in order to find Q, you should know the modulus of rigidity for a shaft material, denoted by C, and the polar moment of inertia of the shaft cross section, and it is denoted by J, and I is the length of the shaft. You don't need to memorize these things. This is just for your knowledge. Here I have given you a worked out example for torsional vibration. Try and understand this example. We'll be doing more questions in your tutorial classes. Okay, so this is the end of the vibrations lecture. See you with another lesson the week after next. Okay.